Hey everyone, it's Bradley Bush again with another algebra video for you. If you are new to my channel, welcome. I'm glad you're here. If you're returning, also welcome. If you enjoy the content you see, please think about subscribing, leave a comment, give me a like, and pass the word along. Today we're talking about solutions to linear systems. So the to-do list, first of all, what is a row operation? That's kind of core to what we're discussing. And then we'll talk about Gaussian elimination with back substitution, and then we'll give you a worked example. Here we go. When using Gaussian elimination to solve a system of linear equations, we can only do three things in our algebraic manipulation, and those are called row operations. Super important. If we can algebraically transform a matrix A into a matrix B using only row operations, then we say that these two matrices, A and B, are row equivalent. So row equivalent just means you can get from matrix A to matrix B just by using row operations. And what are these magical row operations? Well, here they are. The first one, you can interchange two rows. So you have a matrix. In your matrix, you have rows, and you can swap the rows. Just switch them out. And that doesn't change the solution. That's something I should also note here. Row operations do not change the solution to the system. That's why we can use them. So these row operations do not change the solution to the original system. That's why they're allowed. So interchanging two rows doesn't change the answer to the system you're dealing with. The second row operation we have is we can multiply a row by a non-zero constant. That's like saying you have an equation and you multiply both sides of the equation by 3. It doesn't change the answer or the answer you have for the equation. So the third thing we can do is we can multiply a row by a non-zero constant and then add it to another row. So that means you also could just add two rows together and replace one of the rows with those two rows that were added together. So these are the three row operations you can use. What is Gaussian elimination with back substitution? That's the big question here. And the answer is it's a simple method for solving systems of linear equations in matrix form using three row operations. So this shot here, this screenshot here, is actually really fantastic. I wish I had something like this when I was learning this in school, because if I could just take a screenshot of this, maybe with the bottom stuff down here filled in, that's all I would need personally on a test or doing my homework to remind me how to do this whole process. So if you want to just stop the movie anytime in I feel like I just said movie, and I feel like I'm talking about like the Avengers or something, but it's not quite that interesting. If you want to stop the video, that makes it sound a little less interesting. If you want to stop the video at any time during this part where I'm discussing right now, it's actually a great time to take a little screenshot and then print it out and have it by you when you're doing your work, or if you have an open notes exam, use it then. So we start out with a system of equations. And that's just a normal system, right? Here we have three equations and three unknowns. We start by creating our augmented matrix. That just takes the coefficients of the left-hand side that we see here and puts them in matrix form. So we drop all the variables. And then we also put in the right-hand side of the equations too. So you don't technically have to have this vertical bar. Sometimes you see it, sometimes you don't. I put it in just because I think it just helps you visually, but it's not a requirement. Technically speaking, you don't see that. You don't see the vertical bar in a matrix because matrices just have numbers. So after we create our augmented matrix, then we use row operations to go from the augmented matrix to row echelon form. And row echelon form has ones along the main diagonal and zeros in the lower diagonal area. And then we back substitute. After we finish getting our matrix using row operations into row echelon form, or rref, then we back substitute. And you back substitute by putting back in all of the variables once you're in rref. You throw all the variables back in, and then you just solve the system. And it's actually easy now to solve the system because we already have one of the equations solved, right? Z equals 3. We know that. We know exactly what 3 equals because we're staring at it, right? So then we can take that 3 and we can plug it back into Z in equation 2. And then all we have is Y to solve for. Then we could take Y, plug it back in for Y once we solve for Y, and we can take Z again and plug it back in for the Z in equation 1, and we can solve for X. So you're just kind of slowly stepping back up in your system, solving for a new variable each time you take a step. So our first step from equation 3, where we know Z equals 3, is just to solve using equation 2, solve for Y. So we know Z equals 3. So here we have Y minus 2/3 times 3 equals 0. Lucky for us, the 3's cancel, and we're left with Y minus 2 equals 0. We can add 2 to both sides. And what do we get? Y equals 2. So we have just found Y. We know what Z is. We've just found Y. Now we can take those two, which Z equals 3 and Y equals 2, and we can plug them into equation 1 now. So we have X minus, what is Y? Y is 2, plus 2 times Z. What is Z? 3 equals 9. So again, we have 6 minus 2, which gives us a positive 4, equals 9. We can subtract 4 from both sides, and our 4's cancel on the left, and we get X equals 9 minus 4, which is 5. So our solution then is the ordered triplet, 5 and Y equals 2 and Z equals 3. So there you go. That's a terrible square right there. Let me try that one more time. Let's do it red, for crying out loud. Let's make this look kind of... There we go. That's much better. Awesome. So if you wanted to stop now and take a screenshot, might be a good time. All right, so let's show the details now. So I kind of skimmed over one important part. And later you might not be super happy if we don't discuss it. So all of these row operations that got us from the beginning, which is the start, to the end, which was the rref, all of those row operations we kind of skipped over. That is the tedious part of this whole thing. I wanted you first to see a bird's eye view of what's going on, because these row operations that I've just circled in blue are so tedious that you can easily get lost in the forest and not see the forest because of all the trees. So let's come down and see all the gory detail. You ready? Here we go. Ready or not. So we start out with our system of equations. And we have equation 1, equation 2, equation 3. We create our matrix form, which we have right here. Now we start using our row operations. Hope you didn't forget them. This is a part that's really important to be very detail oriented. If you don't label, for example, each time you perform a row operation, then when you're going back, it's going to be a pain. You'll probably just give up and start over. If, say, you have a mistake, you get to the end and your answer isn't correct, you won't be able to go back and find out where your mistake is unless you have been very detail-oriented, very explicit, written down everything that you did with labels. So that's what I do. And I would highly recommend you do the same thing. So row 1 is going to be changed to row 2. Because what I'm going to do is, see, the first thing I need to do here is this element here needs to become a 1. Because we're trying to make this in this equation, or this matrix, we're trying to transform it into rref. So that first element there needs to be a 1. I could just say multiply everything by 1/2, but I think it's just easier to swap rows 1 and 2. So that's what I'm going to do. Row 1 is going to be equal to row 2, and row 2 is going to be equal to row 1. So let's do that in the next matrix. So row 2 is going to be row 1. So I have 1, and I have -1, I have 2, and I have 9. That was the old row 2, and now it's row 1. And now we're going to put in row 1 here in the row 2 spot. Now I have 2, I have 1, I have 2, and I have 18. So row 3 I left, just copied straight down, nothing changed there. So now we're good with that first step. That's great. Now our second step is this needs to be a 0. So what I'm going to do to make it a 0 is I'm going to say -2 times row 1, which if you look at this spot, 1 times -2 gives me -2. And then if I add it to row 2, I'll zero out my row 2 right there. So let's try it. So if we have -2 times 1, that gives me -2. Add it to 2, and I get 0. -2 times -1 gives me +2. Add it to 1, and I get 3. -2 times 2 gives me -4. Add it to 2, I get -2. And -2 multiplied by 9, add to 18 gives me 0. So again, there's a lot of really tedious, kind of mind-numbing sometimes calculations here. So you really have to be really, really careful and pay attention to what you're doing. If your mind takes a mental holiday, which is very easy to in these problems, you're going to make a mistake and it's going to come back later to haunt you. So, great. We've now, we're almost done with the first column, I should say. We have a 1 in the first spot, we have a 0 in the spot below that, and now this right here needs to be a 0. And we will have finished with the first column of our transformation. So that needs to be a 0. So if we say, if we just subtract row 3 and row 1, so row 3 is going to be equal to row 3 minus row 1, then the rest of the two, row 1 and row 2, just get carried down. So I just write them down, and I'm going to change row 3 here. So row 3, let's see, what am I doing? I'm adding. So this is 1 minus 1 is 0. 2 minus a minus 1 gives me a 3. -1 minus 2 gives me a -3. And 6 minus 9 gives me a -3 as well. Awesome. Notice that. Check that out. Our first column is in rref form. So we're on our way, right? We're not done with the matrix, but the first column is good. We have a 1 in the main diagonal and 0s all below it. So now we move down 1 spot, and we move to the right 1, and we start again. So we're at the diagonal, so this needs to become a 1, and everything below it needs to become 0. So let's start with the 1 here. Let's fix this by saying 1/3 times row 2. Meaning we're just going to multiply this entire row by 1/3 and see what we get. going to work out for us. Trust me. So 0 times 1/3 is 0. 3 times 1/3 is 1, which is what we want, right? Negative 2 times 1/3 is negative 2/3. That's not super exciting because we've got a fraction now, but oh well, we'll live with it. And 1/3 times 0 is 0. Perfect. Now our next step is we need to make this bottom element here in the second column, that needs to be a 0. So if we say row 3, which is the current row we're in, is going to be row 3 minus 3 row 2, we'll multiply negative 3 by row 2 and add it to row 3. So negative 3 times 0 is 0. We add it to 0 and we get 0. So that's nice, it stayed. Negative 3 times negative 1, or positive 1 gives me negative 3. Add it to 3 and I get 0. And negative 2/3 times negative 3 gives us 2. And 2 added to negative 3 gives us negative 1. Negative 3 times 0 is 0. And add that to negative 3 and we get negative 3. That's not a good negative 3. Let me try that one more time. So now we are so close. All we need is, we need this last spot right here to be a 1, right? So we come down one step and go right one, and we keep going. So now we're at the very bottom right corner of our coefficient part of the matrix. So we can make that negative 1 into a 1 just by multiplying row 3 by negative 1. So that's what we do. Everything else stays the same. So negative 1 times 0 is 0. Negative 1 times 0 is 0. Negative 1 times negative 1 is positive 1. Negative 3 times negative 1 is positive 3. Now we are complete. We have our row echelon form because we have 1s along the diagonal and our lower diagonal elements are all 0. So now we can return to the system form of our equations and we can back substitute. So let's do it. We're so close, actually. We're really close. The stuff that we just did was by far the most tedious. So we know that 3 is equal to z. So if we plug that back in to equation 2, we could solve for y. So let's do it. We know that z equals 3. If we plug that into equation 2 and solve for y, then that means this little z right there is going to be 3. And the 3's cancel. So we get y equals negative 2. Take the add 2, sorry, to both sides. And we get y equals 2. Now we have one more. We have z equals 3, y equals 2. So we have z equals 3, y equals 2, and we put both of those back into equation 1. So if we say instead of z there, we're going to have 3. And because, sorry, y there, we're going to have 3. I just put the z in. That was an accident. I really meant 2 for y. And here, I need a 3. So 2 times 3 gives us 6, and then we have a negative 2. That gives us 4, and we can subtract negative 4 from both sides, and we get x equals 5. So our solution then to our system is x equals 5, y equals 2, and z equals 3. That was crazy, huh? Awesome. Hope this was helpful. You might want to go back and watch things again just so you kind of get the whole Gaussian elimination process, because it can be kind of tedious, but once you've done it a few times, it becomes just tedious, not difficult. I hope you enjoyed, and thanks for watching.